Hello, today we'll discuss the alternating current in AC circuit. Alternating current in a AC circuit containing resistance. Okay, so we'll find what is the relationship between the current and voltage in the resistive circuit when we apply the AC voltage to the circuit. So we have seen that the nature of the alternating current and voltage, but when you apply this voltage and current to these basic components of the circuits, you know the basic components of the circuits are, it is a resistance, inductance, and capacitance. These are the basic components of the circuits. So we'll see how the relationship is there between the voltage and current when you apply the alternating voltage to the circuit, which is contained only the resistor circuit. So when you apply the alternating voltage to this component, each component responds differently. Each component responds differently. The rise and fall of the voltage and current, they will not at the same time. Here in this resistance, the rise of voltage and current will be at the same time, but rise and fall of the voltage and current, they are not at the same time in case of the inductance and capacitance. First, we'll see how the current and voltage relationship is there in case of the alternating current in a resistor circuits. So we have the circuit like this. We have to, this is alternating source to the load which is having resistance only. So this is, we can see, generator having the EMF source V, and it is the current flowing through the circuits, and it is having resistance R. Okay, so the circuit with resistance only, what is the current I is flowing through the circuit? It is according to Ohm's law, it is a voltage by R. Okay, that is voltage by resistance. But when this voltage is zero, what about the current? Current is also zero. When voltage is zero, current is zero, because the current is proportional to the voltage in this case. That's why when the voltage is zero, the current is also zero. So we can see the phasor diagram of this like this. So the alternating voltage which we apply to this resistor network is like this. This is the voltage and this is the current. So this is the maximum value of the voltage. This is the maximum value of the voltage Vm, and this is the voltage. When you apply the voltage to this circuit, the current will also start flowing in the circuits, but the magnitude of the current is like this. Okay, so this is the current, and this is the maximum value of the current. This is the maximum value of current. Okay, so here current as well as voltage on this axis, and on this axis it is the time. So this is the variation of current and voltage, the rise and fall of the voltage at the same time in case of the resistive circuits. So we can write here Vm and Im. Vm is the maximum value of voltage, and Im is the maximum value of current. Therefore, by using Ohm's law, we can write Im is equal to Vm by R. Okay. Now, but the RMS value of the sine wave is, you know, what is the RMS value of this? RMS value of a sine wave is, it is a point not 0.707 times the maximum value, times the maximum value, means like this. RMS value of the voltage is Vm by root 2, that means 0.707 times the maximum value of the current. Similarly, for the, this is the RMS value of voltage. Similarly, the RMS value of current is I is equal to Im by root 2, equal to 0.707 Im. So we can put this in equation 1. When you put this in equation 1, equation 1 is nothing but this is a Im is equal to Vm by R. What is Im? Im is equal to we can write here Im is equal to, from this equation we can write Im is equal to I by 1707, and Vm is also write V by 1707 R times. We can write like this. So here this term will get cancelled. What will remain? I is equal to V by R. So we can say from this that the Ohm's law can be applied without any modification. Ohm's law can be applied to this circuit without any modification, whether it is a AC or DC circuits. So Ohm's law can be applied without any modification to the AC circuit possessing resistance only, if the resistance is there in the circuit. But we cannot apply the Ohm's law without any modification to the circuit containing inductance and capacitance. That we'll see in the next lecture. So this is how, because there is only resistance component, that's why without any modifications we have to apply the Thevenin's theorem. Now, if the instantaneous value of the applied voltage value of the applied voltage is V is equal to Vm sine of omega t, then the instantaneous value of the current is then the instantaneous value of current in a resistive circuit is R is equal to V by R. So it is a Vm sine omega t by R. So we have to draw the phasor diagram. Here actually the current and voltage, they are in the same phase. Means actually they coincides. It is a coincidence, means it is voltage at the same time it is a current. They are in the same phase, but for the sake of the simplification, I have drawn little bit different. This is a voltage and this is a current. Both they are in phase. So this is a phasor diagram. This is a phasor diagram for a resistive circuit. In this way, this is the resistive networks, and when you apply the alternating voltage to the resistive networks, we can apply the Ohm's law without any modifications. Thank you very much for watching this video. Thanks.